everyone. We're moving into a new unit, but it's not entirely new in that we're using a lot of the same definitions and terms that we've used in previous units. What we're looking at now is objects moving in circular paths or curved paths. Not objects spinning necessarily, but objects moving in circular paths, like a planet going around the sun or a car going around a racetrack. So our goal is to explain that a net force is required to move an object in a circular path. Identify agent and direction of centripetal force. Identify directions of tangential velocity and centripetal acceleration and centripetal force. All right, so let's start by writing down Newton's first and second laws. So Newton's first law is that whole object in motion stays in motion one. An object at rest will remain at rest, and an object, and this next part is very important, traveling at constant speed in a straight line will continue to do so unless acted upon by a net force. So objects will move in straight lines at constant speed unless acted upon by an outside force. So if an object is not moving in a straight line at constant speed, an outside force is at play. If it's moving in a curved path at constant speed, a net force is at play. An external net force is at play. If it's moving in a straight line at a changing speed, a net force is at play. So unless it's going in a straight line and has constant speed, a net force is acting on it. Newton's second law, if you recall, is the equation F net equals ma, or A equals F net over m, where acceleration is the net force acting on an object divided by its mass. So we're going to watch a quick video. There's no audio to listen to here. I'm going to play it a couple times. You can find this link on your own. It'll probably play smoother if you just find the link on your own. We're going to watch it once or twice, and then we'll talk about it. So here's the video. Just going to make it a little bit bigger. Watch it one more time. All right, so let's talk about this video for a bit. I'm just going to replay it and then pause it. All right, so we might come back to it. All right, so before entering the circle, if you will, think about the ball's motion. How is the ball moving before the hammer hit it? It was moving in a straight line. And that's what Newton's first law tells us is going to happen. It's going to move in a straight line at constant speed. But the person in the video wanted to move it in a circular path. So what did they do? You should have noticed they hit it with a hammer. But which way were they always hitting it with the hammer? Don't say up, down, left, right. Think about which way they were always hitting the ball with the hammer. They were always hitting it toward the center of the circle. And when the person stopped hitting it with the hammer, what happened? It moved in a straight line. So go watch the video again. This is a very important concept. So use Newton's first law to explain why you must apply a force toward the middle of the circle to keep an object moving in a circular or any curved path. Without a force toward the middle of the circle, objects move in straight lines. All right, so again, thinking back to that video, the bowling ball is going to move in a straight line unless a force is acting on it perpendicular to its direction of motion that will always point towards the middle of the circle. So here's like a top-down view of the ball. So I'm just going to draw little arrows for the velocity of the ball. So the ball was going this way. At any given point, actually, let me change the color here. We'll go to red. At any given point, the ball's velocity is kind of like this. The arrow is always the same. It was always about the same speed. But the velocity, we would say, is tangent to the circle. Those should all be straight lines. So the important thing to note is the velocity is always changing, and tangent to the circle. It's sometimes referred to as tangential velocity. So some people might say, well, it's moving at a constant speed, so the velocity is not changing. That's not true. Velocity is both magnitude and direction because it's a vector. So if the direction of the velocity changes, then the velocity is changing. It doesn't matter if the magnitude of the velocity isn't changing. All you need to do is change one of them, or both of them, for the velocity to be changing. And if the velocity is changing, then the object is accelerating. So how can Newton's second law be used to explain that an object moving in a circle must have a net force acting on it? An object moving in a circle is accelerating, as we just demonstrated above. Since A equals F net over M, there must be a net force to accelerate the object. So this video here, I'm not going to play it for you, but check out the link. This is an excellent video. It's like 2 minutes long, and it does a great job of explaining what centripetal force is. So what is centripetal force? Centripetal force is the net force pointing to the middle of the circle. Just important to note that centripetal force shouldn't really appear on free body diagrams. It's like net force. It doesn't really appear on free body diagrams. Centripetal acceleration is the acceleration of an object that is moving in a circle. Be careful here. Centripetal force, centripetal acceleration. These are very different than centrifugal Okay, we'll discuss that a little bit later on, what that other term means. But centripetal means center seeking. It always points to the middle of the circle. So what you'll notice here about the directions of velocity and centripetal acceleration and centripetal force. Velocity is tangent to circle, while FC and AC are point inward. So notice how the centripetal acceleration here always points to the middle. I'll draw a couple more of them. My velocity, no matter where you are, is always going to be tangent to the circle. And it's not drawn in here, but I'll draw it in. Centripetal force is always going to point in the same direction as centripetal acceleration, to the middle, no matter where you are. So notice how the centripetal force and centripetal acceleration all change. But think about that for a moment. If you're spinning something on a string in a circular path, the string, the tension in the string, is what provides the centripetal force. Which way are you? Think about the direction you're pulling on the object as you spin it around in a circle. You're always pulling in a different direction. So the direction of the centripetal force is always going to change. So if we were to draw these acceleration, force, and velocity vectors on, let's say, this person in this top cart here, the velocity is going to point this way. The centripetal force is going to point this way. And the centripetal acceleration would point this way. So again, it's really important to note that an object moving in a circular or in a curved path or a circle must have a centripetal force acting on it, a net centripetal force acting on it, I'll say. And there has to be an agent or a cause of the centripetal force. Again, it's kind of like net force. Okay, you can't just say the net force is pushing it. No, things make up the net force. Just like centripetal force, maybe gravity, like a planet going around the sun, tension, like a ball on a string spinning around, friction, like a car going around around a track, or the normal force. Look at these. Look at the roller coaster cars. The normal force would always be pointing perpendicular to the surface towards the middle. So the normal force would be providing the centripetal force in that case. There could also be multiple agents, multiple things causing it to move in a circle. So what was the agent of the centripetal force that kept the bowling ball moving in a circular path? It was the hammer. If I whirl the ball around on a string, what's the agent of the centripetal force? We kind of said it, tension. Just be careful. Don't say the centripetal force is what's making it move in a circle. Specifically, there should be an agent of the centripetal force. One thing I want you to do, try this on your own, is to think at the instant shown here where the object is at M, so it's an object moving in a clockwise circle. I want you to identify the direction of the centripetal acceleration at that point, the direction of the centripetal force at that point, the direction of the velocity vector at that point, and if I were to cut the string at that instant, which way would the object go? All right, so make sure you finish that and submit it, and then have a great weekend.